So we're pleased to have Dr. Ryan Szypowski from Math and Statistics. He's originally from Canada. Did his undergrad degree in computer science at University of Manitoba in Canada. And then he got a master's degree in computer science from University of Illinois at Urbana-Champaign. Then he moved to Southern California to San Diego, PhD in math from UC San Diego. Then broadly, since his undergrad years, he's been working in numerical analysis and scientific computing. And more specifically, during his PhD, he studied finite element method, which is the topic of today's seminar. His study for PhD was finite element method for constrained hyperbolic systems. And he has been a faculty at Pomona Math and Statistics Department since 2011. I think during that time, did you do a sabbatical?
I've done 2 sabbaticals now. One of them I went back to UC San Diego for a year. So yeah.
All right. Help me welcome Dr. Szypowski.
Thank you very much for that warm welcome, and thank you very much, Ayrton, for the invitation to speak at the seminar today. So real quick, I did my PhD in finite element methods. That's where I first got introduced to this idea, this mathematical framework, this approximation technique. And at the time I was studying constrained hyperbolic systems. That's not necessarily supposed to mean anything at the moment. But since then, I've actually gone back more to what the finite element method is usually applied to, which is elliptic PDEs. And so most of my work since then with the finite element method, and even a lot of it at the time, was applied to elliptic PDEs. And so you're going to see a lot today that basically the canonical elliptic PDE that I study as a mathematician is the Poisson equation, because it's a great model for essentially anything that we would want to study and apply the finite element method to. And then, yes, you can extend to much more complicated PDEs, but if you can find problems or understand the theory for the simple case, then yeah. So that's what you're going to see me do a lot today, is solve the Poisson equation over and over again in different ways. I mean, I'm not actually going to solve it, but I mean, you'll see me talk about solving it and things like that. So to begin with, though, I want to do a quick set of disclaimers. So this is a physics seminar. I am not a physicist, right? I'm a mathematician. I have dabbled in physics over my career. In fact, I got into numerical analysis because I was studying geodesics in a curved space-time, and I needed to solve for the path of those geodesics numerically. That's literally where I got my start. It was in something adjacent to numerical relativity, and I love doing stuff like that, but I'm not a physicist. So what you'll notice, for example, is I'm terrified of things like units, and so I get rid of units in everything I can, okay? You'll see, these are just like, okay. So I'm also not a COMSOL expert. So I know that COMSOL is a major tool in how we can, one of the major packages that we can use to apply the finite element method. I am a user of COMSOL. I definitely know some of the things in COMSOL. I have a perspective on how COMSOL behaves that comes from my strong mathematical background, though. So like when I'm looking at the options and stuff in COMSOL, I'm looking at it from the perspective of someone who knows what I've proven theorems about and what I expect to happen, and whether I find or not that button that's going to do the thing I want, I experiment more like a mathematician, okay? But I'm not an expert, okay? I will, if you are working in COMSOL and want to talk, I'd be happy to talk, though. And then lastly, I'm not sure I'm really even a finite element expert, honestly, but it's my field of expertise. So I guess that's what I'm going to talk about. Okay. All right. So you have to start any talk about finite elements with a pretty picture. I didn't know what to do. This is something based on one of the earliest equations that I was writing papers about. This is technically a solution to the Poisson-Boltzmann equation, where the F, E, and M are like molecules with point charges in them, and then there's a solvent around it, but it's just a pretty picture. But it's there to remind us about a few things about the just the idea of what we're studying here. We're studying partial differential equations, which I'm going to spend a fair amount of time just introducing. PDEs are things that we solve, and the solution to those are functions. So what we're looking at here is the function in a rectangular domain, and the color is supposed to represent the height of the function at those points. And that's what we're looking at. So this is what we're going to be studying for the next 50 minutes or whatever. We're going to be looking at problems where this is the kind of solution we would be looking for. So a quick outline, I'll do an intro to PDEs and the finite element method. I'll talk a little bit more specifically about the adaptive finite element method, because that's actually where I've spent the most of my own time researching. I'll talk about a few pitfalls that if you're just a user of finite elements, you might end up in one of these pitfalls. I'll focus on one major one, but there are a number of pitfalls that you might fall into if you're just using the finite element method without really knowing the mathematics behind it. And then I'll spend some time doing some demos. And those demos are going to be in either COMSOL, or I will also very quickly at least show you some Python code using the package known as FEniCS. And so I'll talk a little bit about FEniCS as well. That's what before ever being introduced to Dr. Salik and working in COMSOL, I used FEniCS for almost all of my solution in the finite element world. Either that or smaller packages like written by my advisor originally, stuff like that. So, okay. So what's a PDE? A PDE, the E stands for equation. A PDE is an equation where the unknown thing that we're solving for is a function. It's a multivariable function, so it depends on multiple inputs, x, y, z, t, that kind of a thing. And then the equation itself has that unknown variable. It appears in the equation differentiated, partially differentiated, right? Because it's a function of multiple variables. So we can't talk about just the derivative. That's a PDE, any equation like that, okay? They're used to model tons and tons of things in science and engineering. The first bullet point talks about the three classic PDEs, classic linear PDEs, the Laplace-Poisson equation, the heat equation, and the wave equation. They're classics because they characterize three very different types of solutions that behave very differently. I'll talk a little bit more about that on the next slide. But PDEs are extremely generic, right? You can use them in fluid flow, the very famous Navier-Stokes equation that have major open questions about them, the Schrodinger equation, Maxwell's equations for electromagnetism, linear elasticity, if you want to bend a bar and know what the stresses and strains in that bar are, there's a PDE for that. Fluid flow and porous media, that's a very big topic these days as we pollute our water systems and stuff like that. And dot, 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 goes on and on. Lots and lots of things can be represented through PDEs. Typically, PDEs get classified into three categories. So we name them based on conic sections: elliptic PDEs, parabolic PDEs, and the hyperbolic PDEs. Elliptic equations or elliptic PDEs are generally stationary. They're things that they're static in time. So they would be like if you wanted to study the heat distribution in this room, but not changing. So you assume that you've flowed time to infinity and there's no motion in the room. What corner is going to be hot? What corner is going to be cold? That would be an elliptic PDE. And that would just actually be the Poisson equation or the Laplace equation. Parabolic and hyperbolic equations are time dependent, and they have a very different characteristic. Parabolic equations sort of have like a decay. The heat equation is a parabolic equation. So if you wanted to study the heat and distribution in this room, but as a function of time, that would be, you'd be solving a parabolic equation, whereas the hyperbolic equations are usually wave-like. There's some sort of propagation. There might be loss of energy as it propagates and things like that, but there's much more like direct propagation of information in hyperbolic equations, okay? As I said earlier, most of what I'm going to be talking about today is going to be related to elliptic equations, but the finite element method can be applied in various ways and shapes to parabolic and hyperbolic equations. It's actually quite easy to do it to parabolic usually, where you at least use finite elements in space, and then you just do ODE time stepping in time. Hyperbolic equations is a little bit more challenging usually, but there are techniques there as well. The equations themselves can either be linear or nonlinear, and most of what you'll see is me studying linear equations, because how do we solve nonlinear ones? Well, we just linearize them and we solve them over and over again with small perturbations, and that's how you typically solve a nonlinear equation. You approximate it by a linear one and just repeat, okay? So you'll see me mostly talk about linear PDEs here as well. So what else is there to do with PDEs though? On that picture, you saw that I was solving this PDE just in some rectangular region. We don't normally solve our PDEs like in all of space or all of space-time. We have some bounded domain, which I'm just going to call omega here. And then maybe the problem's time dependent, so then you have a bounded spatial domain and also time going from 0 to some final time. And then if you think back to your ODE classes that you've maybe taken, where you were solving mostly initial value problems, you had maybe a system of ODEs, or maybe just a single higher order ODE or something like that. And then you would, in order to get an actual unique solution to that problem, you'd impose additional conditions on that solution. You'd have the ODE, but then you'd also have a set of initial values. Well, in PDEs, especially these ones like elliptic PDEs, we have what we call boundary values because we impose some sort of conditions around the outside of the domain. If it's time dependent, then we do include initial conditions as well, usually. Okay, these are the typical setups. So, and then there's lots of different types of boundary conditions. I'll throw some names around throughout the talk, but you'll hopefully from the context pick up what they mean then. But the two classic ones would be what are called Dirichlet boundary conditions or essential boundary conditions. Those are boundary conditions where you specify the value of the unknown function just explicitly. And then Neumann boundary conditions, or natural boundary conditions is the other name for those, where you are specifying the value of the derivative of the function, usually the normal derivative of the function on the boundary. And so I'll talk a little bit about those, or you'll see examples of those come up as I show examples of the PDEs later. But so there's a PDE, there is a domain that you're solving that PDE on, and then there's a set of auxiliary conditions like initial or boundary value conditions that the solution then also has to satisfy. So for example, here's the next pretty picture. If I were to solve the Poisson equation, so this is the Poisson equation. This says the negative of the divergence of a coefficient c times the gradient of u is the unknown function here, should equal f, subject to some sort of boundary conditions. If that's what I want to solve, then depending on what you choose for f, what you choose for those boundary conditions, and what you choose for c, the solution might look a certain way. So in particular, this picture, let me talk through that. This is a setup where actually f equals 0. There's no source term to this. All of the energy in the system is coming through this boundary over here. And so along this left-hand boundary, I'm imposing a Dirichlet boundary condition that the solution must be value 1 there. Okay? On the forward and back boundaries, the ones close to us and far from us, but this is plot of the solution as a surface over top of the domain, right? So on this near boundary and far boundary, I'm imposing homogeneous Neumann boundary conditions. So the flux should be 0 through these boundaries. These are insulated boundaries. You can see that the derivative of the solution in this direction is constant. Sort of if you see that it's yellow constantly as we approach the boundary, or it's blue constantly, right? If you follow lines that are perpendicular to the boundary, you see that it's staying constant right near the boundary. That's a Neumann boundary condition. And then I have another Dirichlet boundary condition over here of 0. So the natural profile of this is the temperature should just be falling from temperature 1 to 0. And if everything in the room had the same coefficient of diffusion, then you would actually just see a linear profile. You'd see something that just goes from height 1 to height 0 in a linear profile. But I threw something into the mix by making the coefficient discontinuous in a small square on the edge. The coefficient is extremely large. So it's able to diffuse rapidly. The heat is able to diffuse rapidly in this region, and so it stays nearly constant. And then all of the change is relegated to where the coefficient is small. Yeah.
Oh, Ryan,
Yeah.
for my dim memories of T2E and M, I think that when you set f equals to 0, Poisson's equation has a special name that the
Laplace equation. That is correct. Yes. So this is really Laplace equation. Although even with Laplace, usually you don't even have a coefficient in it. Maybe, I don't know. I think the naming can vary, but yes, exactly. So this is really more like Laplace's equation, where I set f to 0. Yes, exactly. So this is the kind of thing we're solving. This is a much more explicit description of the kind of thing we're solving. And that's all this slide was here to do. I just wanted to point out that this is the kind of idea of what we can apply the finite element method to. And I'm actually going to bounce back to it because I'm going to start talking about, well, then how do we find solutions to these? Or find is a bad word because find suggests like maybe you're doing something on paper and you're just analytically coming up with a solution, which you can definitely do for simple enough PDEs. But for most PDEs, that's not tractable. And so when we say find a solution, we really mean approximate a solution. So as a numerical analyst, I'm really particular about use of the word approximate because we don't compute solutions, we compute approximate solutions. So how do we approximate solutions? Well, there's lots of ways. the typical thing that leads you towards the finite element method is to say, I'm going to look for solutions that are piecewise polynomials. So on my domain, I'm going to assume that the function looks a certain way in this region, and this region, and this region, and this region, and in each of those regions, it's a polynomial. The simplest case of this would be something like a piecewise linear function, which is in fact actually what that picture was. You can't tell, but that picture is actually a piecewise linear function. It is, if you were to zoom in on this picture at any place, there is actually a flat plane that is representing the solution, and it's just that the triangles that are making that up are so small that it looks smooth, and then also the graphics are pretty terrible as well, but then also like there's shading, and the shading is smooth, and so it looks really smooth, but if you were to zoom in, it's actually faceted. It's actually a bunch of flat planes making up this solution, okay? So they don't have to be flat planes. They could be flat little quadratics or something like that with little bumps in them. That's viable as well. Like these are all like things that you can do with the finite element method. But again, the lowest order case is usually piecewise linear, although I'll be talking about piecewise constants as well. And so you could ask the question, well, maybe I can't find this really complicated function, but maybe I can find a piecewise polynomial that is close to my solution. And so how would you do that? Well, first of all, if it's going to be piecewise polynomial, it's got to be on some region, it needs to be a polynomial. So you take your whole region, your entire domain, and you split it up into something, small elements, I say here. In one dimension, small elements would just be small intervals. In 2 dimensions, there may be like small squares or small triangles. In 3 dimensions, there may be small cubes or small tetrahedra. You basically take your domain and you split it up into these things, okay? This is what's called meshing, and that's a very important element of the finite element method, but this isn't the finite element method yet. The idea of doing that, that's not enough, okay? And then on each element, you assume that the solution looks a very specific way, like a polynomial, okay? So this third bullet, I say, but this poses an interesting challenge. So imagine, so let's go back to this picture. I'm telling you that that is actually a faceted surface where every piece of it is a linear function, really. And so now imagine taking that and plugging it into the PDE. This is a linear function. Like it isn't overall, but anywhere you could like analyze it, it would be linear. It's perfectly flat. So let's imagine taking that and plugging it into the PDE. What would happen? It's linear. So when I go to take the gradient, what kind of thing is going to come out of the gradient of a linear function? So think about in one dimension if you need to. If I differentiate a linear function, we get a constant, right? So the result of this is going to be piecewise constant. Okay? I told you C was also piecewise constant, so this product is piecewise constant. And now I'm going to go take the divergence of that. So in one dimension, I'm taking another derivative of that. I have a function that is piecewise constant. So it's flat here, and then it's flat here, and then it's flat here, and it's flat here. And yeah, I'm going to go take its derivative again. What am I going to get if I differentiate a piecewise constant function? You're going to get 0 everywhere that you can do it, right? There's also a lot of places where you can't even compute the derivative because there's a jump discontinuity in it, right? Anywhere that you can, you're going to get 0. So yes, I kind of lied. I said that I put 0 on the right-hand side. I didn't lie. I put 0 on the right-hand side. But if I hadn't had a 0 on the right-hand side, then there's no way that this function could have solved this equation because the result on the left will always be 0. And if f weren't 0, then there's no way to get equality here. So yes, this picture is with f equals 0, but I could have done f equals non-zero, and yet it would have still looked just as nice. I would have still just been just as happy with my solution. So something's changed. We don't solve that problem. That is clearly not the equation that I find a solution to, okay, when I apply the finite element. So what do I find a solution to? Well, this is called the strong form of the PDE. It's called that because it has strong conditions applied to the unknown function. In order for this to make sense, you have to have enough derivatives that the left-hand side makes sense. So you would have to be like C2 or something like that, twice continuously differentiable or something like that. It's made a little bit more complicated by the fact that C is discontinuous. So, but something, it'll need to satisfy some conditions so that it's differentiable enough. And I'm trying to find a solution that isn't differentiable enough. So that's what the last bullet they were saying. It's saying that the second derivative would have been 0. So what do we solve instead? We solve what's called the weak form. We weaken the requirements on U. How do we do that? Well, I'm going to do this in one dimension because this is where everyone in the room can do the calculus, okay? Otherwise, it would be vector calculus and I get lost myself, okay? So, all right. So in one dimension, this is what this problem looks like. It is just looking for a function u whose second derivative is given by some fixed function f. I put a minus sign here. You guys may not. I'll fight you about that if you want, but no. So this is the Poisson equation in one dimension, and then these are the particular boundary conditions I'm going to talk about right now. But again, this is all just for illustrative purposes. It's not like this is the only problem we can solve this way. And so I chose boundary conditions on the left that are Dirichlet, so they fix u's value, but on the right they fix u prime's value. I'm doing this so that's a Neumann condition. I'm doing this just so that you see the effect of both of those in when we derive this weak form. How do those two different boundary conditions impact what happens here? Okay. So step one of arriving at the weak form is to say, I'm going to test these equations against something. I'm not going to just assume, I'm not going to like evaluate them at a whole bunch of different x's. I'm going to test them by taking an arbitrary test function b, that is the terminology we use. We're going to call u, I might call u the trial function, and then I call b the test function here. So we're going to take a test function. I'm going to choose an arbitrary test function. It will have one requirement. Because u has a Dirichlet boundary condition here, I'm going to require that b satisfies that same homogeneous Dirichlet boundary condition. So it's not completely arbitrary, but it's that. It's going to have to satisfy that and more conditions that we'll see in a minute. And I'm going to multiply the differential equation by it, and then I'm going to integrate over the domain. You might say, well, why would you do this? Well, there's an implication that's at least true here. If u satisfies this, then u satisfies this. That direction is at least true, right? Because this equation was true, I'm allowed to multiply it by a b and integrate, and it should still be true. Nothing should have broken the truthness of that statement. And so this is clearly true for all choices of b, okay? There's a huge question of, well, if this is true for all v, is this true? And that is yes, the answer is yes to that. You can prove this using some analysis. And so take some math classes in upper division math classes about analysis to see this. But basically, with enough conditions on b, this does imply this. It does go backwards as well. Okay? Okay, we haven't weakened it yet. I still need two derivatives on u, right? I haven't solved the problem yet. This is not the weak form. So what's the problem? I've described that the problem here is that if u is going to be piecewise linear, u double prime is going to be 0 everywhere it's computable. So this is the bad term, right? This is the term that I need to get rid of somehow. So what do I want to do? I would really like if there weren't two derivatives on u. So does anyone know a way when you're handed an integral and inside that integral there's something that's differentiated? Do you know an integration technique that lowers the derivative on one term in a product? Integration by parts. We're going to integrate by parts. So the rule of thumb in the finite element method and just PDEs in general, if you're going for a weak form, is multiply by a test function and integrate by parts. Whatever that means, if you're in higher dimensions, you're using a Stokes or a Green's theorem type thing, but it's just integration by parts. It's all integration by parts. So if we integrate this by parts, that negative u double prime is going to become a u prime, and we will have differentiated the other part, so the v will become a v prime. So the vdu or whatever part is going to be this, right? And then it's an integral on a domain, so we're going to have to evaluate something on the boundary, and in particular it would be this u prime v would need to be evaluated on the boundary. We now see why I included in v that I'm going to enforce v of 0 is 0. I do that so that when this term gets evaluated at 0, I have no idea what this is, but I know this is 0, so it vanishes. When x is 1, I don't know what v of 1 is, but remember one of the boundary conditions was that u prime of 1 was 0, so I do know that this is 0 and it vanishes. So both terms here vanish for different reasons. One vanishes because of the boundary condition on u at the right, and the other one vanishes because of the boundary condition I imposed on the test function v at the left. This, by the way, is why the terms Dirichlet and Neumann get called essential and natural. V was the boundary condition at 0 was an essential boundary condition because I had to bake it into v, into the test space, whereas it was natural that the upper term was going to vanish because the Neumann boundary condition handles that. It handled itself naturally. So at the end of the day, after imposing those boundary conditions, this is the equation we're left with. We're left with, look for a U that satisfies this for every choice of V. And we're now starting to see that that term, every choice of V, is a little bit misleading, because clearly something has to be true about V. We see what we do to V in this equation. Well, so there's definitely two things that have to be true about V. V needs to be able to be underneath an integral sign after multiplying by stuff. So we need to be able to integrate it, whatever it is. But we also need to be able to do something else with it, right? Differentiate it, okay? So there we go. So yes, it's not every possible function V, but at least a lot of functions. For example, piecewise linears. So, so at the end of the day, our weak form is this problem. The full problem in weak form is find U in some space V. I'm just going to be very vague about that, such that the integral from 0 to 1 of U prime V prime equals the integral from 0 to 1 of FV for all V in the space. To make this more rigorous, I'd have to define what the space V is. That would require a discussion of Sobolev spaces and Hilbert spaces, but that's the idea. That's where we're at. That is the weak form of a PDE. So this is what I'm going to approximate solutions to, not the original strong form of the PDE, okay? So that's where we're at. There is another way to derive this, by the way, that might be more interesting to you if you view problems from an energy perspective. If your PDE really came from minimizing some energy, then this can pop out from that approach as well, where you're just using calculus of variations, and then V is sort of like the variation, right? So, all right. Let's move on though. So that's the problem that we're going to solve. So how then do we approximate it? Well, the simplest thing to do, this problem I still can't solve exactly, because V is an infinite dimensional function space. I can't describe all functions that satisfy this in any easy way, not with some basis or anything like that, which is what we really want. So we're going to replace V by a finite dimensional space. And if we do that, then using our linear algebra ideas, if it's a finite dimensional space, then there's some basis for it. There's some set of functions out there, phi 1 through phi n, that when I take all linear combinations of them, they span VH. So then what I do is I don't look for a U in all of the V, I look for a U in the span of this set of functions. So that means I'm really actually just looking for some coefficients. I'm just looking for UIs. I turn my problem from a problem about finding a function into a problem about finding a vector. Just a bunch of numbers. I just need some numbers. I need some UIs. What do they satisfy? Well, they satisfy the fact that when I plug this into the equation, this equation is satisfied for all V. But it can't be all V. That's too many equations for the n. I only have n unknowns, so I need n equations, right? We've done some linear algebra. We know we probably want the same number of equations as unknown. So what do? Well, I also restrict V to be in that same finite dimensional space. This is what's called the Galerkin approach. There are other approaches where you might choose different spaces for the test and trial phase. This is the classic Galerkin approach. It's what you'd see most often in the finite element method. And then by linearity of everything here, we can use these basis functions to rewrite this in another way. That's much, much more natural. So the equation finally becomes this. I'm really just looking for a vector U with components UI, I running from 1 up to n, such that those numbers times these numbers summed up equal these numbers for every j. What is that? That's just a system of linear equations, n linear equations in n unknowns. It's got some complicated numbers in it. This is just some number. This is just some number. These form the coefficients of the matrix in the problem. So these things here are the coefficients. When you choose an I and a j, you're getting the thing that goes in row I, column j of a matrix. When you choose a j here, you're getting something in the jth entry of a vector. And then you're just solving a times a vector equals a vector. That's it. We've converted from a PDE, complicated partial differential equation, into a linear system of algebraic equations. Okay? That's something we have a lot of tools to solve. We toss this into something that computes solutions to AX equals B, like MATLAB or anything else, and we get a set of U's. And then if we want the function, we just have to go back to the span that we did a minute ago. We just have to go back to this formula here, where the solution is represented as a particular linear combination of those functions. Okay? So it all comes down to that. This still isn't the finite element method. This is just a Galerkin method. So what makes it the finite element method? Well, the finite element method is a specific set of choices for these basis functions. We still haven't come back to that yet. This works no matter what basis you pick, what finite dimensional subspace you pick. The finite element method is all about picking piecewise polynomials or similar types of things for those basis functions. So in one dimension, we might take our domain 0, 1 and split it up into subintervals. These would be called the elements. There's an element from 0 to 0.2, from 0.2 to 0.4, so on and so forth. And on each element, you define a set of basis functions. If I'm doing piecewise linears, then my basis functions, I would have one basis function associated with each node. So there's a basis function associated with the node at 0. What basis function is it? It's the one that's linear on the element that it's on, goes from 1 to 0, and then it's 0 across all other elements. Then there's a basis function associated with 0.2. That's the function that's linear on the two adjacent elements, goes from 0 up to a peak of 1, and then back down to 0, and then it's 0 on all the other elements. So each of these colors, the blue, the red, the green, the magenta, the black, and the cyan, are each different basis functions. So if I take a span of all of these basis functions, I get the set of all piecewise linear functions that are piecewise linear on that mesh. Okay? And I look for a solution in that space. All right? That's the finite element method. In higher dimensions, those basis functions look more complicated. This is a depiction of what a basis function would look like in higher dimensions. If my domain has been triangulated, so I have a two-dimensional domain, there's some triangles down here, then associated with every vertex in my mesh, there's a basis function that's 1 at that basis function, and it drops linearly to 0 on all the neighboring elements, and then it's exactly 0 outside this patch. That's the basis, that's the piecewise linear basis function. In 2 dimensions, I can't draw the picture in 3 dimensions. I need to be able to do it in 4, right? So, but that's the idea, okay? So, and this is the piecewise linear case. It doesn't have to be piecewise linear. You can do piecewise quadratics, piecewise cubics, lots of other things, especially when you get to vector valued unknowns where, yeah, it gets complicated, but that's the basic idea. So, yes, Ertan.
So for example, COMSOL,
Yes.
what is the default choice? Is it usually linear or?
I believe the default in COMSOL, every time I have done something for the Poisson equation, it always picks quadratic. It always steps up by 1. And I always drop it back to linear because I like them best. I don't know why. It's because that's where I'm just the most comfortable in all the theory.
And does that how much does that affect the computation time?
So we can talk about the number of degrees of freedom. So if so then this depends on 2D versus 1D versus 3D in some senses. If you're in 1 dimension, then the number of degrees of freedom for a piecewise linear is just equal to the number of nodes in your mesh. And then if you step up to quadratics, then you have a degree of freedom at both endpoints of every interval, and you also have a quadratic bump function. So the basis functions if you're doing in 1 dimension for a quadratic, you would say, I'm going to write this. So the finite element language is we don't work on a small element. We work on what's called the reference element. So the reference element would say just be the reference interval 0 to 1. And then on that interval, you will have 3 basis functions. Do I just have white? Maybe. So one basis function would be 1 at this left endpoint, and then it would have to be 0 at this middle and the right, and it's quadratic, so it would look like that. Then there's a basis function that's 0 here, 1 here, and 0 here, and it's quadratic. And then lastly, there would be a basis function that's 1 here, 0 here, and 0 here, and it's quadratic. And you might ask why we make these choices. It's simply so that the UIs have an actual meaning. They are pointwise values of the function. So yeah, you would end up with this. So now how many degrees of freedom do you have? Well, you still have 1 per node, but you also have 1 per element. Okay, well, that's actually not too bad in 1D. That's just twice as many unknowns minus 1 or something like that, right? But in higher dimensions, if you go to quadratics, you'll have 1 per node. So on the reference triangle, you'll have 1 basis function per node, and you'll also have 1 basis function per edge, which we can use some graph theory to understand. Again, it's something like it's twice as many, or it's something like that. But it actually depends, because once you get into 2D unstructured meshes, you can have lots of edges maybe, or few edges, but still the same number of nodes, that kind of thing. Just depends on the topology of the mesh. So it definitely steps up the number of degrees of freedom in your problem. And it does buy you something in the convergence, but not it. So I don't have a good answer for you in that I'm not gonna tell you not to use quadratics. I'm definitely not gonna say that. Because, and in fact, what I would tell you is the best thing to do is to pick your polynomial degree and your mesh together. This is what's called HP adaptivity. And that's going to be the most optimal thing you could do, but that's very hard to do. So you definitely can use any degree you want that's meaningful. Generally speaking, there's a rule of thumb, which is the higher degree the polynomial, the better it is at approximating something that's smooth in the region. And then if it's rapidly changing, then you might as well lower the degree of the polynomial and just shrink your mesh. So put your degrees of freedom by shrinking the mesh down, instead of putting your degrees of freedom in a way where you put them on the edges, that sort of thing. I could talk more about that later. I already led to this though, which is the finite element method doesn't just put a mesh, put the basis functions and solve. That's the basic finite element method. But instead, in order to get a more accurate answer than we had a second ago, we iterate a process. We adapt the mesh or the polynomial degree. So this is the classic structure of the algorithm for what's called the adaptive finite element method. So what is the adaptive finite element method? Well, we're going to start with an initial mesh. Okay? We're going to solve, quote unquote, the problem on that mesh to get something that I'm just calling UK here. Then we do a step which is interesting. So this is one thing I always harp on when I teach numerical analysis. We are approximating solutions to things. So there's exactly one thing we can never know. We can never know the actual error in that, because if we knew the error in that, if we had an approximation and we knew the error in that approximation, then why don't we just add those two things and get the exact solution? But we don't know the exact solution. That's why we're approximating the problem, right? Approximating the solution. So we never know the exact solution or the exact error in our solution, but we can use fancy mathematics tricks to be able to estimate the error by, say, a number. So what we can do is say, in this triangle, we could say, somehow this triangle is attributing 0.5 to the total error. This is a process called error estimation. More specifically, a posteriori error estimation, because we are using the current approximate solution to do that. So we're doing it after the fact, hence a posteriori. We are doing that. We estimate the error, and we get what are called error indicators. They're not error values. They somehow indicate what is contributing to the error being large. And that's what these etas are supposed to represent. We then look at our mesh and we say, okay, these triangles over here and these ones over here, they're contributing the most error. Let's make them smaller. That's called marking. You say you're going to make them smaller, and then you actually do that. So then you say, okay, I want to make those triangles smaller. I will refine those triangles, and the mesh will become a new mesh, and I will repeat this again. Because the mesh is now finer, I expect my solution to be better. I expect my estimates to be better. I expect this procedure to work. And this is the mathematician in me now. It's not just that I expect it, I can prove it. This algorithm is provably convergent for a huge class of PDEs. Okay, so this is where like the mathematician in me would spend another 5 hours talking about the theory behind that, but I'm not going to bore anyone with that. Okay, so I just go through those steps individually. Solves the problem. I do want to point out we don't ever actually even exactly solve the individual problem we have, because solving AX equals B is hard. You're going to make errors just when you're doing that. Okay, so the method is robust to that. And I'll talk a little bit about that when I get to COMSOL. Estimating, like I said, it's to approximate the error. Let's move on. Marking is, in the theory, it's usually done by something called Dörfler marking. But again, when I get to COMSOL, you'll see they don't use this terminology. They don't do exactly this, and it still works. And then finally, refining. This is just to show you that classically in the theory, we use a refinement technique called newest vertex, but that's really hard to implement. So most people implement longest edge. And so the idea is that every time you have a triangle that's been marked for refinement, you're just going to cut it in half. But notice what's going to happen if I do that. There's a neighboring triangle here, and maybe I didn't cut it in half. So now there's this node hanging in the middle of an edge. We can't have that. We need our meshes to be what are called conforming. And so even though this triangle was marked for refinement and maybe this neighbor wasn't, this neighbor might get refined too. So more than just the marked elements get refined. But yeah, that's that. So, all right. I should probably start doing demos soon, but this is getting to some pretty pictures. This is the pitfalls section, and I'll just talk about this one pitfall because of time. There's a big issue when you're using the finite element method, which is choosing your function space. So for simple enough problems, you can probably just head into COMSOL, have it do its defaults, and you're going to be fine with that. But if you are solving a PDE sort of more the way I do, which is I don't think of the physics first, I'm sorry. I think of the math. And so I go in and I'll actually show you the interface I've been using most in COMSOL, and you guys might get mad, but it's just the reality. I have to pick my finite element space very carefully because I can't necessarily just rely on COMSOL's defaults. And maybe you shouldn't either as a physicist. I think there's a conversation to have there at least anytime you're choosing these, because I can show you how badly this can go. I'm going to solve a very simple problem very poorly. I'm going to solve the Laplace equation again, the Poisson equation again, but I'm going to do it in a different form. I'm going to do it in what's called the mixed form. I'm going to introduce a second variable into the problem. I'm going to use the unknown from before, but I'm going to introduce its flux as a second variable. So I don't just want to find u, I also want to find its flux. Well, one way to do that would be to find u and then differentiate u and get the flux. Or I can put them both in as unknowns into the original problem and solve for them simultaneously. So that's what I'm going to do here. If I convert to the weak form looks like this. You now have two test functions, p and tau. And so this has to be true for all choices of tau and all choices of v. And now the reason I'm doing it this way is now I not only have to pick a function space for u and alone, I now have to pick a function space for u and sigma. And there were a lot of really bad choices for that in combination. So here's the first bad choice. I've been harping on about how good piecewise linears are. If I were to approximate both u and sigma by piecewise linears for this choice of exact solution, this is, by the way, again, the mathematician in me is that I build a problem so that I know the answer. It's cheating, I know, but it's the best thing to do, I think. So for that specific solution, this is what I get if I use piecewise linears. The true solution is in red, and my approximate solution for sigma is this curve, and my approximate solution for u is this one. And you might say, oh, that's a pretty coarse mesh. I'm using a very wide mesh. I've talked about the fact that you make the mesh smaller to get a better answer. Maybe I just need to make the mesh smaller. Maybe the fact that I'm getting these terrible oscillations is just that my mesh is too big. Okay, let's make the mesh smaller. Okay, maybe we just make it small enough yet. Maybe we just didn't make it small enough yet. Maybe we just didn't make it small enough yet. These oscillations will never go away. This is an instability caused by our choice of function space, of finite element space. There's nothing wrong with the math. There's nothing wrong with, there's something clearly wrong with the math, I mean, but there's nothing wrong with the ideas of what we were trying to do, but it doesn't work. Okay, let me give you confidence by showing you that it can work. By the way, I'm labeling this slide CG1 plus CG1. This continuous Galerkin 1, Galerkin from that term I mentioned earlier, continuous because it's piecewise, but because it is continuous, you see, and then the 1 because it's linear. Piecewise linear continuous functions is what I'm using here. To give you hope that this can be done, I'm going to choose a different pair of spaces, and it works. Now, you have to give up on something here. I'm going to use DG0. D stands probably for discontinuous. So C was continuous and D is discontinuous. So now notice I'm going to approximate this red curve by a discontinuous curve. And then I'm going to use continuous but linear over here. And even on this coarse mesh, I'd say that's reasonable answers. We don't like piecewise constant functions, maybe that they feel dirty. But if you just refine the mesh, they get better and better. So by there, the blue dots are on top of the red dots. I think that's pretty good. So that it can work. I just had to pick a different function space. But just to show you that it can go wrong other ways, if I tried piecewise constants, that wasn't the fix. Because if I also tried piecewise quadratics over there, then you still get instabilities. Okay, that's enough of that. Okay, so let me quickly, because I have like 5 minutes left, right? I want to load COMSOL at some point. Okay. I want to show you two things. I want to show you what FEniCS code looks like, just so that you you know, this is how I used to, okay, that's unreadable, but it's basically Python code where you type in actual like stuff about the weak form and things like that. So down here, let me show you this at least. This here is me defining the weak form. So this A equals u dot dx of 0 times v dot dx of 0. This is saying u prime times v prime integrated dx. So you literally, in FEniCS, you build in your weak form, and then you just say, solve my problem, please. So, and it does it. So that's FEniCS. It's very useful. It's what I used for most of my career. But what does COMSOL look like? COMSOL looks like this. So COMSOL is where you can do actual physics, I think. You can do it in FEniCS. People do. You can go to the FEniCS website, by the way. I've got the FEniCS website over here if anyone's interested. It's just a, like I said, it's just a Python package. You can go there and see that people are doing actual real simulations of like fluid flow problems and everything like that. But in COMSOL, if you're wanting to do some of this stuff, then the way you're going to do this is you're going to set up the physics that you're trying to solve. And you will notice that this is what I was meaning. I am almost always these days just using the weak form PDE, which is almost certainly what most people in the room would not be using. I like that. I like having to write down what my weak form is. So I know I'm actually going to apply it to the Poisson equation, but I'm not going to do that by clicking on the Poisson equation stuff when I make this problem. I'm going to click on weak form, and then I'm going to go and type in the weak form.
So we add physics there.
Yeah.
And you're adding.
Let me show you. So when you go to make one of these models, you go to new model wizard and you say you want to do a 1D problem, let's say. You folks are probably clicking on like, oh, I want to do some acoustics, and I don't know what any of that stuff is. I want to do some math. I want to solve some PDEs. I want to do that in the weak form. That's what I do. There's a bit of a lie because I also was using, when I was doing some of the classic PDEs, I also go and say, I want to solve the Poisson equation. But I don't think about what physics that's representing. I just think about the math. So how do you use COMSOL? You do exactly this kind of stuff. I'm gonna go back to one of the ones I had a second ago, and just show some neat things. Where's the one that I kind of want to show? Let me go to open and grab this one. So I made this problem because it actually did something I did in a paper years ago. I wrote code myself in the paper, and I was like, oh, I want to see what COMSOL looks like this. So what this is going to solve, I'm just going to walk through a little bit here and then point out some of the things in COMSOL. This is a Poisson equation. So, and you'll notice here, it is actually a Poisson equation. It's not a weak form of a Poisson equation. So this is a Poisson equation, but it is a Poisson equation with a weird coefficient. So this is me defining the coefficient. And you probably can't read it, but the coefficient I will tell you now, because the geometry tells me the coefficient. This is also where, if I was an expert in COMSOL, I wouldn't do it this way. I'd do it by defining a material, but I have no idea how to do it. So I'm going to solve on a cube, but then there's an inset smaller cube. So this is a 1 by 1 cube, and there's a half by half cube. I'm going to have a large diffusion coefficient in this small cube, and then a small diffusion coefficient in the outside part. That's what we have. And you then define boundary conditions. So then my boundary conditions are along this face and the far face. It's 1 here and 0 here. And then all the other 4 faces, it's natural boundary conditions, going on insulated boundary conditions. And then you build a mesh. And so let me show you the mesh I built. And when I say you build a mesh, I mean you click a button and it builds a mesh for you. But like I did nothing for this. Though, again, as a mathematician, I do one thing, and that is I always move away from the default on element size, and I always go to extremely coarse, because I don't trust COMSOL to build a good mesh as a first step. I trust the math to build a good mesh. I trust the adaptive finite element method to build a good mesh. So I'm going to start with a coarse one, and then I'm going to let the adaptive process build up a finer mesh. That's how I always do it. I don't know. This is just the mathematician in me again. So I start with an extremely coarse one, and so this is the mesh over here. Whoops, trying to spin the picture. So there's a mesh. It's got a bunch of tetrahedra on the inside that we can't see. And then I go down to the study that we started, and this is where I turn on the magic, which is I turn on adaptation. So by default, it's not on. I turn on adaptation and error estimates. Here's where I go with the defaults, and that's just because I can't find the thing I really want. As a mathematician, what I really want is I want residual-based error estimation, and then I want Doppler marking for my refinement and stuff like that. I go with the defaults, and they seem to work. They work kind of more rapidly, but you set that up, and then you go back up here on home. Where is it? Maybe on study, I have to go over here, and you compute. You hit the button, and this is on my tiny little laptop. This is maybe not a good idea, but oh, no, it's actually running pretty quickly. It's going, it's going, it's going. It gets slower because the mesh is finer. That's right. Yes. Yeah. So yeah, with COMSOL, you can see like how well this is converging. You can see how many degrees of freedom there are in the problem, all this kind of stuff. And so this is a slice through the solution at the end. And so we see that in this small cube where the diffusion coefficient was large, the function's fairly constant. It's basically red throughout this whole region, but it still decays down to 0 outside. And here you see it decays down to 0 outside. That's what you can see here. I'm much more interested in the meshes. So if you start looking at the meshes, some interesting stuff happens. This is one step of adaptivity. Here's another, here's another, here's another, here's another. And you're going to notice something happening here. The mesh is getting more and more refined around this point and this point. And that's where the discontinuity in the coefficient is. Here's the best part of COMSOL. You can say, well, I want to see inside. So you just hide this thing. Let me see if I can figure out how to do that again. I go to the geometry. I hide. I find a button. I hide the small cube. Did I do that? Not hiding. It's not working. Ayrton, do you remember another way to hide other than selecting it? Maybe I right-click on it and say hide. Is there a hide somewhere in there? Oh no, I did something with Zoom now. Okay, right-click.
Well, there is the wire.
Yeah, it's okay. All right. But anyways, what I was going to do is I was going to show quickly that one of my plot groups was supposed to be the mesh itself. Part of the problem is I did these simulations on my desktop, so I didn't have to wait too long. And then I copied them over here, and I think the graphics on this are actually much worse. So I think it's slow to draw stuff is part of the problem. Oh no, I think what's happened is I've hidden everything. That's what I think has happened. I really have hidden everything. Right click. That's not it. Let's just try to hide just this one and then go down. It's possible that that's what happened. Yeah, there we go.
Yeah.
Okay. Yeah. I figured it out. I went to defeat it. So I hit that cube, and you see that in fact it refined a lot along this edge, a lot along this edge, and it didn't refine as much here, but it started to refine more and more as it went in. And again, that's because we had Dirichlet boundary condition here, we have Neumann here and here, so the physics is different here. And so, yeah. Anyway, this kind of stuff is what I do for my own work. Is I study this sort of thing. I don't usually care about much about the physics, but I care about the mesh generation. I care about what comes out, that kind of stuff.
So,
Yeah.
when we solve it with the default choices,
Yeah.
COMSOL doesn't do adaptive.
By default, it doesn't. You'll have to go into the study and turn it on. Yeah. And again, there's a question of how much time you have, right? So I started my mesh course and I let the adaptation make it finer and finer and finer. You don't have to do that. You could start with a fairly fine mesh and then do just like maybe 1 or 2 steps of adaptation. I start with a really coarse one and I did 10 steps. So that's another thing I had to change, by the way. To get it to do 10 steps, I had to go down here and say, I'd like the maximum number of adaptations to be turned on. By default, it's turned off and then the default is low. I turn it on and I say something much larger. So I do that sort of stuff when I'm using COMSOL. But again, I'm using COMSOL from a very different lens than most physicists in the room probably would be using it. Maybe I'm giving you good advice. I have no idea. Because I don't know how good it is for the physics. I know it makes me happier as a mathematician though. That's what I go for. I just want to be happy. Okay.
So
yeah.
I think for standard problems that I assigned in wave optics and E&M, those are very simple problems. I think default choices are perfectly fine.
Probably
I
perfectly
think
fine.
the issue is when you have a complicated structure with very thin nanostructures or these nanocubes, nanorods, whatever, then obviously you need some sort of this. Then because otherwise it will just average over things, or you know, it will not look at the details there unless instructed to do so.
Yeah, there's actually even something else that I'll point out. If your problem is complicated enough, and say it has a source term that is a fairly complicated function, as you saw, when you're building the weak form, it has to compute integrals. So numerically, what tools like this do is they use Gaussian quadrature to approximate those integrals. So Gaussian quadrature is just a technique for approximating an integral. And it's very accurate, but it has limitations. So for example, one of the problems that oscillation one, I don't know if you noticed the graphics for that were in MATLAB. I coded that by hand because I couldn't get COMSOL to do it exactly the way I wanted, because the numerical quadrature was introducing its own errors. Because the right-hand side function has a blow-up, and it wasn't computing the integrals accurately enough. So there was basically some energy loss when I was doing it in COMSOL. So yeah, like being careful about these things, knowing the limitations of the software, that kind of stuff is going to be critical. Yeah.
Just to step to an even more high level, kind of like why this is so important.
Yeah.
I wish Thora Wheeler were here, because she is a much better expert on this sort of thing than I am. But in a huge range of simulation problems, even not even when you're trying to solve some analytical equation, but when you're trying to simulate something in physics or astrophysics. I could take Coral's research, which is simulating galaxies over cosmic time. You have this huge problem because you're trying to simulate a system that's enormous, but a lot of the action is happening very small locations within it. So it's completely prohibitively expensive to divide the whole box of the universe into these really, really tiny elements. You have to somehow figure out where is the action, and you make your simulation boxes really tiny there, like within galaxies, or even within like certain parts of galaxies, or towards the middle. And then you make it much bigger outside, and you pass things on from boundary conditions up and down the scale. So, you're clearly tapping into it's not at all boring to think about how do we carve up the cube like this.
Right.
I see adaptive mesh refinement has its own acronym AMR. It litters the literature. It's like everywhere.
Yeah, and there's multiple techniques. So this is all the finite element approach, but maybe you're going to do a finite volume approach, and then maybe you're going to use cubical meshes, and then you're going to use like an oct tree to do local refinements. Like these 8 cubes are inside these 8 cubes are inside these 8 cubes. So there's all sorts of stuff that you can do depending on what techniques you apply, but they have similarities to all these other things. Let me point out one last thing in COMSOL. If you are, like I said, the other thing I always change is I always go back to piecewise linears. If you want to do that, that's where the discretization is. So in the physics, you go over to the settings for the physics, and there's a discretization there. So Lagrange is just another term for this idea of building your basis functions like this. And then you could choose quadratic. Oh, accidentally, I think I was on quadratic, folks. You could pick linear, or all the way up to septic degree. You can change from Lagrange to different ones. So for example, I had talked about using discontinuous ones. So you can use discontinuous, piecewise polynomials, any sort of other thing. So yeah, those are all in there. Nodal serendipity is something that a postdoc of mine had been working on in the office with me when I was at UCSD. So I know a little bit about it, but it's just another way to describe the basis functions. It's all neat stuff. It's all cool math. I don't even know if I had any more slides in my talk. I must have, but let's just demos. That was the slide. I had a slide that said demos. So I think I'm done. I can show people more things in COMSOL and stuff like that if anyone's interested, but yeah, that's all I have for everyone today.
Almost out of time, so very quick questions from students if they have any. Seems like, yeah.
You know anything about any sort of I guess machine learning or neural network research in helping out these approximations?
So there is current research being done by various people, not myself, who are trying to solve PDEs by training. So what you do is you train a machine learning a neural net on like, here's the inputs to a Poisson equation, here's the outputs, train it on that over and over again, and then you say, okay, well now what's the solution to this one? And they are getting results that are reasonable. I also know people, so at the end of the day, all that comes down to, and I didn't talk about it here, all that comes down to is approximation theory. Piecewise polynomials, the reason why as a mathematician I like them so well is because I can prove theorems about how well you can use a piecewise polynomial to approximate an arbitrary function. And so I didn't write the theory down, but like there's, order h or order h squared or these things where h is the mesh size. I can write the theorems down. Machine learning, neural nets, they're just a way to do very complicated function approximations. That's all they are. And so there was a colleague at UCSD who was studying the mathematics of neural nets and machine learning and trying to prove the theory that's necessary for how well can they do at approximating functions, just like we did with classic numerical analysis 60 years ago or 80 years ago, where we were doing polynomial approximation. So they're trying to fill those gaps. And so people are definitely doing that. They're either doing the theory like I'm referring to now, or they're just in practice doing it and they're seeing good results. So yeah, definitely it is probably where things are moving, right? That's going everywhere, right?
Yeah.
We all know that. Yeah. Anyone else?
One last question, if you have any. Okay.
That's a funny question.
Oh yeah, funny question.
ahead.
Sure. That's fine.
Mathematician.
Yeah.
What's your favorite field of physics?
What's my favorite field of physics? Astronomy. I don't know. Is that broad enough, or is that narrow enough? Astronomy. Okay. Yeah. Is that a field? Did I just stir something up by calling? I don't know. I'm worried now. I don't know. Are we okay with that?
All right, so physics students know this, but other students would not be acquired